Last time we had some visitors. Oh, it's making me nervous. Back to you guys now. So last time I defined for you a vector space. It's a set paired with a notion of addition. Scalar multiplication subject to these 10 axioms. All right, and let's see here. What I failed to tell you last time was that from those axioms you can derive some very sort of natural things. In particular, if you have those vector space axioms, it then immediately follows that the scalar multiple of 0 in any vector is again the 0 vector. You're like, well, it doesn't have to be that way. I'm telling you, we can prove that point by point in the axioms, okay? So if you have the axioms, you get these things without any additional assumptions. Any scalar times 0, the 0 vector is a 0 vector. Minus 1 times a vector, scalar multiple, is equal to the additive inverse of a vector, all right? And finally, we get this wonderful cancellation property. If you have a scalar multiple times a vector, I guess I'm missing a dot here to be notationally consistent. I use juxtaposition here. Maybe I should write c dot x just to be consistent. The scalar multiple of a constant and a vector is 0, then either c is 0 or x is 0. Now, for those of you who are currently in number theory or have maybe remembered some modular arithmetic stuff, that number 4 is really kind of precious to us because there's lots of problems where you don't have this cancellation. Just because you have a multiplication of 2, you guys have been multiplying matrices, right? I can't just cancel if I have, forget about number theory, how about this course? A times B is equal to A times, well, let's see here, yeah, A times C. It does not necessarily imply that B is equal to C, right? You need to know things about A in order to make that happen. If A is invertible, include I'll give it to you. My point here is I make no such assumption about C. The only assumption here is that C is a scalar and X is a vector. If the product is scalar multiplication of C times X is 0, then either the scalar is 0 or the vector is 0. And here you can have A times B is equal to 0. Product of two matrices be 0. And that doesn't mean that either one of these is 0. Far from it. It could just be that the columns of one and the rows of the other just don't happen to match up, and you get a product of 0, even though the vectors are not 0. And that's totally possible. Yeah.
Well, I don't know if this quite applies, but if you, like, you know, in our homework we have one where a set of commutable matrices and prove whether or not it's a subspace. Subspace.
Subgroup?
Yeah.
So, anyway, but yeah.
That doesn't mean though if you prove that, then if you multiply any of these two matrices together.
These are not matrices.
Yeah, that's what I'm saying.
I mean, my point is this is a scalar, it's a real number and a vector. So
Yes.
okay, so let me just show you how they're proved briefly. I don't want to eat up too much class time, but it's, and I guess I will, I don't know, I have to debate whether or not to actually put these on the test. It's kind of depressing when I do. So, proof of first of all, I have a lemma, the law of cancellation. If x plus a is equal to y plus a, then it follows that x is equal to y. In other words, you can cancel a. All right, this is true because the addition forms an abelian group, basically. But here's the specific proof. I want you to notice that we're arguing axiom by axiom, point by point here to establish this truth. So if I have x plus a is equal to y plus a, right, by axiom 4, I can find an additive inverse minus a, right? So then I can add minus a to both sides, like so. I use associativity to regroup the additions, right? That's axiom 2. Associativity, I can regroup the things, but hey, by definition of additive inverse, this is 0 and that is 0, so I have x plus 0 equals y plus 0. But then axiom 3 tells me how 0 behaves. That's supposed to be what? X, typo, sorry. And this is supposed to be y. There's one, see, Dr. Professor Landon right there. Tell me about that one later, right there. Anyway, x equals y. So there we go. Law of cancellation. If I have x, I can cancel vectors additively. Okay. And then to prove 1, you got to do something sneaky. So 1 was that 0 times x is a 0 vector. So what I do is I take 0 times x and I add 0. that's equal to 0 times x, right? Because if you add 0, it's the same thing again. But on the other hand, 0 is 0 times 1 plus 1 because 0 is a real number, and 0 times 2 is still the real number 0, right? So then I can distribute by the, well, this is just, this is that the scalar multiple of the scalar multiple is the same thing. So it's the I don't know what the word is. I call it maybe associativity of, no, it's not that. I don't even know what to call it. It's axiom 6, yeah. Anyway, so then you use the distributive property with respect to the scalar multiplication, break it up into two pieces. Then I use the distributive property with respect to the scalar multiplication again, but with respect to the 0 to break it up into these two pieces. And then undo what I did to get 0 times x plus 0 times x is equal to 0 times x. But that says that 0 times x is 0 by cancellation, by the level. Once you have that, it's not hard to prove. Number 2, again, c times 0 plus 0 is still c times 0, but I can change 0 to 0 plus 0. Again, then gives me this, which, so if I have this is equal to that, that shows me that c times 0 is 0. But again, I'm using the axiom in each step to justify what I'm doing. All right, so I'll let you read the other one. It's, well, I don't know, the third one and the fourth one are a little bit sneakier. On a given day, if I'm too sleepy, it might take me a couple hours to get these. I don't know. It just depends. I don't know if there's a, I mean, when you're working with axiom systems, you just kind of have to have some good common sense about what you're doing, what you're trying to use. And things like multiply by 1, you know, multiplication by 0, creative ways of rewriting 0 and 1, basically what comes out to be.
There's a priority of like the axioms that like we should memorize in order to do these proofs. Like, I mean, obviously it's ideal that we know all of them, but like the first 4, like for example.
You need to know all the axioms, yes.
Oh.
Now the reason you need to know all the axioms is because the axioms are your principal weapon for showing something's not a subspace. All right, so let me turn the lights on here and got that on the system. Again, I think it's good for you guys to read this, but I don't want to eat up too much class time on it because it's somewhat disconnected from most of the other things we do in here. But it's important to see these kinds of axiom point-by-point proofs, right? So, for example, Christian, suppose I told you that W is, let's say, I don't know, 2 by 2 matrices A, B, C, D, such that what? Some condition. I'll just say A is greater than 1. B, C, D free. And so here's the question: is W a subspace of R 2 by 2? So this kind of question, I mean, here's the zen for the problem, if you like. I mean, the sort of, here's my personal opinion. It is really hard to come up with examples of vector spaces built on inequalities. I mean, there's probably some way to abuse this comment of mine and find an example, but by and large, if your example has an inequality or a square or some nonlinear function as defining the thing which is alleged to be a subspace, it's probably not a subspace. Now, how do you prove something's not a subspace? Well, if it's a subspace, that means it's a vector space with respect to the inherent ambient vector space structure. And here, the ambient vector space structure is understood to just be addition of 2 by 2 matrices. Standard addition and scalar multiplication you guys already learned, part 1. So you got your choice. I mean, all those axioms, you can pick on any one to try to violate. Which one do you want to pick? I mean, I like the 0 axiom. Which one was that? 3? Axiom 3, yeah. So axiom 3 says that 0, 0, 0, because I know that this is 0 in 2 by 2 matrices, right? 2 by 2 is 0 is this, right? And you notice that 0, 0, 0 is not an element of W, as A equals to 0 is not greater than 1. Right? So that the zero matrix doesn't satisfy the condition for the subspace, game over. So knowing those axioms gives you the power, the knowledge you need to prove things aren't subspaces. Okay, that's why you need to know them. No, I don't expect you to memorize them number by number. It's enough for you to state them, like 0 has to be in the vector space. If you didn't know that 0 being in the vector space was axiom 3, I wouldn't care. In fact, I would rather prefer that you didn't refer to it as axiom 3 when you're working out the test. I would prefer you say there's no 0 in this space because the thing which would be 0 doesn't satisfy the condition of the subspace. That's the argument I would like to see.
For problems like this, we use other axioms, like instead of like.
Yes.
Yeah.
What would you use?
I was thinking of using. I don't have it memorized by like number, but like it was going to be either A9 or A10, whichever one it was. It said that like 2 of them added together would have to equal something. But like I was going to do like 2 0 0 0 minus 2 0 0 0 to equal a 0 0 0, which A I would have done that. That's what I would have done, even if that's even.
So that's.
Which is axiom 10 or 9.
Right. So you're like this. I guess it's a combination of things, but I guess
Wait, hold up. No, never mind. Because -2 is actually not in the thing because -2 is not.
Yeah, I don't think that's a direct check on the axiom, but it goes back to the same thing I just did, so it's not.
No,
Anyway, I will agree with you, Christian. There's many other
You do
things.
2 minus.
There are many other things you could do. That's true. Like scalar multi. Here's a simple thing. You could take A, B, C, D, and W, right? And then consider the negative. Right? It's pretty easy to argue that that's not an element of W because if A is greater than 1, that implies that minus A is less than minus 1. Right? Which of course implies that minus A is not greater than 1.
So there's no additive inverse.
Right, there's no additive inverse. But there are other things you can do.
Like you could have to do a constant that's negative.
Yeah, I'm not. Anyway, one it just takes one. Just takes one. So, yes, sir.
When doing these, though, if you think it is a subspace, then how, I guess for the ones like axiom 1, 2, like they're not 0 or adding to 2 things. Those 3 ones, like real numbers, you just kind of say those real numbers, like just other axioms follow.
Yeah, you can use comments similar to the ones I gave in the notes for proofs as a sort of generic comment. Thanks. So let's talk about this theorem. I stated it last class. I want to go through the proof with you really quick here. Well, not too quick, but these vector space, we have a subset, all right, which is non-empty. Then that subset is a subspace, all right, if and only if the following 2 conditions hold true. It's closed under the addition, and it's closed under the scalar multiplication. All right. Now, to prove something's a subspace, our definition of subspace is it's a subset, which is again a vector space with respect to the inherited operations of the larger set. Okay, superset if you like. So the proof is kind of tedious, but let's look at it. First of all, it's an if and only if proof. Yes, sir.
Is the subset symbol you used there the correct one?
Yes.
Or can it be subset or equal to?
Yes. I mean, I will use W subset of D and W subspace of D. Yeah. And if I wanted to say proper subset, I could say this. If I wanted to say proper subspace, I could say this. Yeah.
But in the theorem, you use proper subset. That symbol. I was wondering if that was right or.
And then last class you didn't use proper subset.
Oh, that's not significant. No. That could be this. I'm sorry. Yeah, this could be. There could be the equals here. Yeah, that's a typo. Dr. Professor Landon, make a note. Thank you. Very good question. So yeah, that should be.
I remember to do it too. I was like,
Shouldn't do that.
You could do that if like you could project on the board without like a projector, like the screen being down.
Yeah, I should do
It would be intuitive, like, but we can't do that.
Okay, so if W is a subspace of V, what does that mean? It means it's a vector space with respect to the operations on V. So therefore, it is closed under addition and scalar multiplication. So that direction of the proof is kind of like, duh. Okay, that's part not hard. How about the other direction though? Why does it suffice to know that if 1 and 2 hold true, that you get the others? Well, okay, so suppose W is not empty. Let's go through it here. Once you understand one of these points, the rest are kind of the same. Just stretching.
Yeah.
Okay. Suppose W is not an empty set, which is closed under vector addition and scalar multiplication. All right. I'm going to pick on. I'm going to work on associativity and commutativity here. All right. So let X, Y, and Z be in W. All right. If they're in W, that means that they're in V. Why?
It's W is a subset of V.
W is a subset of V, right? Now, first of all, we also know that then because they're in V, we know that X plus Y is equal to Y plus X. Why? Because V is a vector space, so addition commutes, right? And I also know that it's associative because V is a vector space and the addition is associative, right? And I also know what? I also know that these are vectors inside W because we've assumed 1 and 2. We assume that X plus Y is again in W, and if X plus Y is in W, then X plus Y plus Z is also in W. So this is all happening in W, and that shows that axioms 1 and 2 hold for W. Yeah?
If you have a subspace, does that automatically mean that you have a vector space? Like that's like the base of a subspace?
Yeah, the definition of a subspace is that it is a subset, which is also a vector space with respect to the natural inherited vector space structure, which is there from the superset. And all the other axioms are kind of the same argument. Basically, the argument is pick a point in W, observe that it's also in V. Now let's go through this one. Okay, so by 3 of theorem 6.1.9, we know that minus 1 times x is minus x, right? But by 2, we're assuming that this is in W, right? We're assuming that scalar multiples of anything in W is again in W, so that means that this is in W. But these are equal by the theorem I just went through. Therefore, that's a W, which then shows W is closed under additive inverses. There's another axiom down. And you just keep going, and you can check each axiom one at a time, one by one, and you can always get it simply from the simple theorem we just proved before from the law of cancellation of lamp, and the assumption that it's closed under addition, scalar multiplication. Here, I'll look at another one. Let A and B be real numbers. Notice that by axioms 5, 6, 7, and 8 for V, we find this. All right. But then what? That means that they also hold in W. The proof is kind of like, I don't know, it's not that surprising. Nevertheless, this is a very, very powerful theorem, right? Because we are trading what? We're trading the trouble of checking 8 axioms for the trouble of checking 2 conditions. Well, 3 conditions really, right? What's the third condition? You need that the set is not empty. Non-empty, closed under addition, closed under scalar multiplication. That's it. So here's the algorithm, basically. This is not, well, okay, there's 4 conditions. I'm sorry, I'm an idiot. Oh well.
This is a whatever, also there's an error of you.
Right. So it could be equals there, yeah, right. So, of course you need that it's actually a subset. Usually this is so obvious we don't even write anything down about this. Right? I didn't even bother to tell you that this set W was a subset of 2 by 2 matrices. It's a set of 2 by 2 matrices, so of course it's a subset of 2 by 2 matrices, like, duh. So it takes a kind of special example to make this point interesting. But there are examples. Anyway, so let's go on.
I actually wanted to copy that.
Want to what?
I actually wanted to copy that down, but it's already.
Oh, it's remark 6.2.7.
Sorry.
All right, so let me put this away and show you some examples of that. Thank you. Oh, yeah, I pressed on. Sorry, I wanted to write this stuff out, but I can't find my notes this morning. I don't know where they went. So let's just look at a nice example. The subspace there. How about this? This is kind of an important example. You can define what's called the null space of a matrix. So let's let A be a m by n matrix, okay? What's the null space of A? Yeah, didn't stay in.
Oh.
I know. Sadly. So the null space of A is very simple. It's x in something or something such that A times x is equal to 0. So where does x have to live? 0 is an example.
And the reals.
No, I mean yes. What dimension? What kind of column vectors? Multiplying
And
n. Yes. That's all I was fishing for. It's either n or m. You know, this is n. Okay. My claim is that that's a subspace of Rn. Now I'm going to take what Landon said is right here. So here's that's my claim. Here's proof. First, I'm going to take Landon's advice and notice that A times 0 is equal to 0, right? So therefore, 0 is an element of the null space of A, which of course then is non-empty, right? You say, well, why do you, I mean, it's just my custom, most people's custom. Look to see if 0 is in the set. That's just an easy thing to check to show it's non-empty. You got to show something. Why not pick on 0? If it's a counterexample like this, maybe you'll figure out, because a lot of times I'll ask you prove or disprove that this is a subspace. So if you look for 0 and you don't find it, hey, done, game over, not a subspace, right? Game's not over, let's go on. So consider, let's say x and y in the null space of A. All right, and C, a real number. I'm going to be efficient in the way I argued this here. Okay, so A times, let's say, Cx plus y. A times Cx plus y. I'd like to show that 0. If I show that 0, that shows that C times x plus y is in the null space of A. All right, so properties of matrix multiplication, right? C times ax plus A times y. I don't know what to say, matrix multiplication, I suppose. Let me just say properties of matrix math. Seems suitably vague. Let's see here, A times x is what?
0.
0. A times y?
0.
0. I don't need vector space axioms here anymore. Now I'm just working with column vectors, right? I know that the sum of 0 vector is again 0 vector. Even without that theorem we looked at earlier today. Aha!
And that proves two.
how did you know that A times y is 0?
We assumed that ax equals to 0 and ay equals to 0 as x and y are in the null space of A. So by definition of null space, that means that A times x and A times y are 0. That's what it means to say that x and y are in the null space. But then, this, Cx plus y, is in the null space, right? So cx plus y in the null space of A. If we set c equals to 1, then x plus y is in the null space of A, right? And if we set y equals to 0, then cx is in the null space of A, right? Hence, the null space of A is closed under addition and scalar multiplication. Thus, null space of A is a subspace of Rn by the subspace theorem. Yes, sir.
So just one specific example, if A was just a zero matrix, then like the null space would be all of Rn.
It is true. If you have the zero space, the null space is all of Rn. That's right. Yeah. Can anybody think of the exact opposite example?
Yeah, if the null space contain
Only 0. What would that be? What matrix would be like that?
Invertible.
An invertible matrix. A specific example, how about the identity? Right? Ix equals to 0. What x solves that? X equals to 0. But you're right, an invertible matrix will also do. Aha! I think we have found yet another equivalent characterization of invertibility. Comment. So, talking about a square matrix, right? Oh man, the marker is, oh no, it doesn't have long to live. It's got lots of juice, but, oh man. I hate that. It's going down into the, I'm going to try to make it work here. A inverse exists. Stay with us. If and only if, I can write likely. If and only if the null space of A is the set just containing 0. Not equal to 0. The null space is a set. It is the set containing 0. There is a difference. Maybe I have some tweezers.
I tried my pencil.
I hope for sharing any tweezers, but
Tired.
you thought about it.
I was
It's
too
you thinking about it.
I know.
Like
it's
the draws
happening.
of lines for the 4 markers.
Yes.
It's okay. Honestly. Okay, so there you go. It's a good example of a null space. Yep.
You said there's a difference between the set of 0 and then the empty set? Is that what
There's
you're saying?
the set containing 0 is a set with an element in it. Empty set is, it's harder to find the element. Yeah. By definition. If the existence of the empty set bothers you, you have a friend here, go talk to Mortis. I don't know. I don't know about that. Are there any other examples I can think of right off the top of my head? Or, I mean, there are tons and tons of examples. Let's see here. How about this? Another example you might like. Consider W equals to f of x in, let's say, twice differentiable functions over the reals such that the second derivative of x is 0 for all x. Okay, so you could write this more compactly as f prime prime equals 0. In other words, I'm saying the second derivative is the 0 function. So maybe I should really write f here to be more consistent. So the function f. So twice differentiable function such that the second derivative is identically 0. Okay, so to show this is not empty, I mean, you got lots of choices. We could use the 0 function. How about that? I mean, I'm kind of tired. I don't want to use 0 function. Let's use something different. How about x? F of x equals to x. Is this in that set? Well, what happens if you calculate f prime prime? You get 0, right? What's the change in the slope of a line? 0. Yeah. So that implies that f is an element of W, which shows that it is non-empty, right? To show something non-empty, you just got to find one thing in it. Non-empty. Now what do I have to check? So let's let f and g be elements of W, and c be a real number. So then what? I gotta check. I'll be lazy. I'm gonna use. What's that?
You have to check this for the multiplication and division.
Right. So again, I'm gonna be sneaky and try to do both at once.
Just like that other stuff.
Ah.
You can do it. That was the CX.
Final. Eventually, find out where it works.
No, it would be more like that. See to have.
CF plus G. I have to calculate the second derivative of those, right? But you guys took calculus 1. You know how the properties of derivatives work. So this is the same as C times F prime prime plus G prime prime by calc 1. But hey, both F and G are in W, and by assumption, F prime prime is 0, and G prime prime is 0. So what do we have?
C0 plus 0.
Yeah, C times 0 plus 0, which is 0. So therefore, CF plus G is an element of W. So if we say C equals to 1, we get F plus G is an element of W. If we take G identically 0, we get C times F is an element of W. Now here, there's a hole in my proof right here. I don't know, actually, that the 0 function is in the set. So there's kind of a gap here. Oh, wait a minute. Yes, I do. I just proved it here. Never mind. Duh. Sorry. We get CF as an element of W. So then, hence by subspace theorem, we conclude W subspace of, oh, I forgot to give this larger of C2, twice differentiable functions on R, which I argued was a vector space by the subspace theorem last class. I mean, one second. This, of course, is a subspace of the just functions on R. Yeah.
So C2 means twice differentiable functions.
It means twice differentiable with continuous second derivative.
Okay, so C n of R would be.
You can differentiate n times, and that nth derivative is itself continuous.
Okay.
So for example, C0 is the set of continuously differentiable functions, which should unfortunately be distinguished from the set of differentiable functions, functions which merely have a derivative, but that derivative might not be continuous. Which, anyway, this is in calculus, so let me not talk about that. If it's something that kept 19th century mathematicians up at night, it's probably not the sort of thing we should talk about too much in passing. So there's seriously quotes about like them having nightmares about that sort of thing. So it's true. Not making that up. Okay, so there's another example. Let's go on.
I have nightmares about math all the time.
My favorite thing Isaac's doing right now, Isaac just turned 4 like a day or 2 ago, but he's always like, do you remember in my dream, blah, blah, blah. It's like, I mean, how do you... the things I'm starting to remember, but it's just that he told me about it before. I was Godzilla in the water, I was flying. Yes.
I love flying rings.
Yeah. Something about Godzilla, something about flying. Let's see here. All right. So another theorem is this: if W is equal to the span of say V1, V2, Vk, where V1, V2, Vk are elements of some vector space V. Then W is a subspace of V. I will refer to this as the span theorem. This, or maybe the span is subspace theorem, because that's what it says. I love this theorem. It's just too easy. Let's prove it. So how can you, let W be so advertised? And I'm assuming that the Vk are as in the theorem. There's, it's clear enough it's a subset of V, right? Why is it clear that it's a subset of V? If I take vectors and I add them together finitely many times, right, and I scalar multiply those vectors, then by the axioms of the vector space, we again get vectors in the vector space. So it's clear it's a subset. I would argue you can supply the details if you want, but that's clear. Now, to show it's non-empty, you got a lot of different things. How about let's pick at the 0 for a second. How do you get 0? How about this? 0 is equal to 0 times V1. That was one of the boring things in the theorem I started with today. All right. There it is though. So that's a linear combination. Scalar multiples of vectors in the spanning set, that's part of what the span includes. Span is all possible finite linear combinations of the vectors. In particular, that includes all possible scalar multiples of vectors in the spanning set. So that's in the span. Right, so W is not empty. So consider X and Y in W. I'm going to use the summation notation here because it's convenient. Then there exists, let's say, Ci and Bj in the reals, such that what? Sum I equals 1 to k of C I Vi is giving me x, right? And on the other hand, y is equal to a sum of other coefficients, Bj, j equals 1 to k of Bj. That's the definition of the span, is that if x and y are in the span, I form them from a linear combination of the vectors that form the span. Okay? Now what do I gotta do? Use the subspace theorem. Just check that a linear combination of these linear combinations is once more a linear combination. Yes, sir?
So might you expand the summation notation to do this?
No.
No? Okay.
I might not.
Might not.
Yeah. Okay, so getting to the point here, I mean, maybe I know I landed, I'm not sure what you mean yet. So consider C a real number. Well, I'm using some other C. Let's pick some other real number. How about alpha? Alpha real number. So let's look at alpha x plus y. What do we got? We have alpha times the sum. I equals 1 to k of Ci Vi plus, and I used a j, but I might as well just use an I. I equals 1 to k Vi, right? That doesn't matter. You can either use I or j. It's the same set of vectors. That's just notation. I could have put an I here to start with. It wouldn't have made anything different.
not J. Oh.
No one would have noticed if I'd done that. No, you noticed. Oh well, my bad. Okay, so then what? Properties of finite sums, which we proved earlier. We can pull that scalar inside, like so, and we get alpha ci vi, I equals 1 to k, plus the sum I equals 1 to k of vi vi, and then one more step. The sum of the sum of two sums is the sum of the sums. In other words, this, which is really just regrouping terms in a sum. It's not terribly complicated what I'm doing here. Right? But then what can you do? You can rewrite that one more step, one more step. So I've got alpha ci plus vi all times vi. What is that? Well, that's, what is this? I mean, let me put it in words. This is a linear combination, the finite linear combination of v1 through dk, right? Therefore, this is an element of the span, which is what we call W. Now what do I do? To finish the thought. Finish the thought here that alpha equals to 1, and then you get x plus y is in W. And if we let y equals to 0, then we get alpha x is in W. Thus, W is a subspace of V by subspace theorem. So the subspace theorem gives us yet another theorem, which I would call the span theorem, because the outcome of it's kind of anticlimactic. If you can write something as a span, it's a subspace. End of story. Now other texts will take a different definition of span. Like I took a pragmatic calculational definition for you guys. It's a set of all finite linear combinations. Other books will define the span as the intersection of all possible subspaces which contain a given set of vectors. That's equivalent. Now in that definition, is the span a subspace? Well, it's the subspace because it's the intersection of other spaces, but we took a different viewpoint this semester, which is perhaps not as pure. Is everybody here today?
Yes.
Looks like 1, 2, 5, 6, 7, 8. Looks like okay. Let's look at an example. Don't worry, there's still time for the quiz. I'll stop this. So here's an example. And so my other example today, we defined null space, all right? I'm going to define another important, that null space example is not just an example, that's something we keep with us. So don't view that in the same way you might view like for example, the example I did, I'm using example too much. The W at the start with A greater than 1, that's got no name, I don't know what that thing is, I just made that up. Null space, that's a go-to thing we use to conceptually understand what a matrix is as we go forward, okay? In the same sense, this is more than just an example. The column space for col A is equal to span, all right, of column 1, column 2, column n, okay. So here I'm assuming that this A is a m by n matrix, okay? So, keeping it real today again. Now, I'm going to claim that that's a subspace of what? Nanu.
N.
Nanu is incorrect. This is a subset of this is in fact a subset of Rm. If you have an m by n matrix that has m rows and n columns. So for example, if I had A11, A12, A21, A22, A31, A32, so this would be a what? A 3 by 2 matrix, right? You see, the number of rows is the dimension, is the size of the columns, right? Each column is a three component vector. I mean, yes, there are 2 columns, but in fact, it's a subset of Rm. So my claim is that the column space of A is a subspace of Rm. Proof. Column space is a span inside Rm, period. Students have gotten this wrong on tests before. I ask, is the column space a subspace? They don't know. It has happened. Perhaps it will happen to one of you. I hope not, though. So, time for your quiz.
So how are we taking this?
Get out a sheet of paper. And I have 2 questions. One is W is equal to X, Y, Z in R3 such that, all right, X plus Y plus Z is equal to 1. W is a subspace of R3. Prove or disprove? Number 2, W is equal to the span of 1, 2, 3, 4, 5, 6. You know, W is a subset of R3. Prove or disprove? I'm trying to help you guys out. So this one is worth 5 points. This one's worth 15 points. Okay. Trying very hard to help you. What?
Do I need to record this or just like?
Did you already turn it off?
No, not yet.
You can turn it off now. It's fine. I think we're done. It's fine if you recorded it. It doesn't matter.